it's kind of like that here. So from another perspective, we define security in the following sense. First is correctness, of course. So which means if you possess the satisfying assignment, you should always succeed. Okay. And then no impersonation, which means that if you do not possess any satisfying assignment, you cannot succeed. Okay, so even if you have like 5 credentials, but 5 is not enough, then you cannot succeed. And then anonymity is the same, in the same sense. So this is our this is from the definition. So given that this is a very, very like a 10,000 feet high-level description of the signing algorithm, which took me some hours to figure out, but it's not very difficult. So the basic idea is that first you traverse the circuit or the policy, and then you know whether you are legitimate or not, right? If the circuit, the output is true, then you know, yes, you are authorized, right? So then, for some technical reason, you need to kind of discount or forget some credentials which are not necessary. So by necessary, I mean if you know a subset of the credential, as long as they are, you can just use a subset of your credentials as long as it corresponds to a satisfying assignment. Okay, so you figure it out, and then you kind of discount the others because they are kind of redundant. Okay. And then you, from bottom up to the root, you for each input wire to the leaf gate, you do kind of the standard or the sigma protocol. You make some commitment, okay, and then you calculate the challenge. Use some ideal hash function or random oracle, which then the output is affiliated with the output wire, the root, and then you kind of just traverse. Top-down, breadth first order, and then you kind of how to calculate the challenges for each input wire of each leaf gate, so that they are consistent in the sense that they are consistent with the gates. If it and you do certain way, if it or you do certain other way, and if it is threshold, you do certain other way. Okay, and then you further bottom up. So it's kind of, yeah, we will show the exact complexity. And then finally you have kind of completed kind of annotation of the policy circuit, and so that is signature. So this is basically very high-level description of the signing algorithm. And for the verification, you mainly check the consistency, the challenges, how are they shared. So by each gate, for each gate you check they are consistent, and then for the input, each input wire to the leaf gates, you check it is really valid or consistent with the challenge and it was a commitment and the response. Okay. So here is the copy of the algorithm. You cannot see it. We don't see it. So here is a security analysis. We can prove that any strongly secure assembly identification scheme is also secure assembly identification scheme. So the arrow means imply. And we can prove that security of assembly identification scheme is equivalent to security of assembly signature scheme. So what is missing is just this piece. If we can prove that our assembly identification scheme is strongly secure, then immediately it means that it is secure. So if it's secure, then the signature scheme is secure. So all the properties are rigorously defined. So we formally achieve what we want from a security perspective. Here is the performance for the signing algorithm. It's not that bad, but overall the size of the signature is proportional to the size of the policy, right, or the circuit. Okay, and particularly the very time-consuming modular explanations, it's just proportional to the number of input wires to the leaf gates. So that's still okay. Of course, if we can get it rated, that's better. So that is actually one very interesting future work. And the communication complexity is just kind of quadratical. So it's still not that bad. So yeah.
Invoking the instances of the Sigma protocol, isn't that big order of B O of B? What is B?
B is the total number of input wires to the policy. So the total number of input wires to the leaf gate.
No, but this is only invoking them. But then they may be expensive protocols. The Sigma protocol maybe is expensive, so there should be another bullet saying how much each one of the protocol instantiations costs.
Oh, okay. Yeah, that's actually a very good point. Fortunately, the thing is that over such scheme right now we can achieve constant size. So yes. So in that count, so yeah, but it's a good point. Yeah. So they are all can achieve as a constant. For example, in the case of group signature, even if you want to prove your wire among 1,000 people, so the complexity is still constant.
But if you run a zero knowledge proof on proving your license plate or your license, your ID, it is not that simple. It's a complicated procedure.
Not really. At least in this specific context, it's really cheap in the sense that just a constant number of multiple explanations. So for the verification, we have kind of a corresponding complexity measurement. Okay, and then we can actually, so because the main issue is that the complexity is kind of proportional to the size of the policy circuit. So we can achieve a little bit better. So we can do this at the particle level. So by which we mean that we can kind of prune the policy circuit. So of course this will be the price is paid as a kind of privacy degradation. So before the policy is pruned, so the potential size occurs as in the specific scenario I mentioned, say 1,000, right? But if you prune the policy, then the potential size could be 500. So you kind of degrade the privacy guarantee from 1 over 1,000 to 1 over 500. So there is a trade-off, okay? And indeed, our signing algorithm has a heuristic to give you how to prune it. So it's not a problem. However, if you want to achieve optimal, then you have to solve some NP problem. Okay, so it's easy to find some reduction from there. So, but in practice, then it should be good enough. I'm trying to wrap it soon, so we have more time to discuss. So another approach to improve the privacy is that is a primitive level. Indeed, for not many, but for some credential schemes, we can actually prune the scheme. So the nice thing is that when you use those credential schemes, standard one, you don't need to do it. But if you kind of doing this, which is kind of overlay, so you build the standard system, use some high-level applications, then you can do that. So that is okay. So this is another approach to improve performance if you're really concerned about it. And there is another issue. So far, those schemes, they cannot allow the law enforcement to hold those bad guys accountable because everyone could be the guy who just requested the access, okay? Because they really hide very nicely in information security concerns who they are. So sometimes we need a revocation, which